Hi everyone, how are you? Can you guys all hear me? It looks like some people had some snow. I hear that some people can hear me, and it looks like our main thing is starting. Just gonna hang on a second because our tech team is gonna put me up. Whoa, looks exciting. I'll just ask our tech team, could you please take the other one down, please? There we go. I think we're here now. Hi everyone, how are you? Welcome to our YouTube channel. Welcome to our live solve. We're very happy to be collaborating with Math Kangaroo. Again, this is a monthly collaboration. We do this every month on the first Sunday of the month. And we're happy to collaborate with Math Kangaroo because I go around and give a whole bunch of talks. I'm a math professor at Carnegie Mellon University, and for 10 years I was the national coach of the math team for the United States. But nowadays I'm very interested in trying to help more people become really good at solving problems they haven't seen before. And one of the most common questions I get is from people who have elementary school kids who want to know what's a good source of challenging questions for elementary school kids. I always say, go to Math Kangaroo. That's where the action's at. So we're very, very happy to do this collaboration where we have two incredible solvers. Actually, I recognize one of them from last night when we were doing AMC8 problems together, but he's awesome, and the other one, Leo, is also awesome. They'll introduce each other in a moment. But what I'm here for is I'm going to introduce our guest from Math Kangaroo. I'll introduce Amy, and after I introduce Amy, I'm actually going to drop out because I got to do the same introduction for the grades 6, 7, 8 live solve. So I'll do an intro, I'll disappear, Amy will pass it on to Eli and Leo, and then they'll take it from here. Sound good? So let me tell you a little bit about Amy. Is it possible for our staff to put Amy's, well, I can do that. I can put Amy's also here on the spotlight. Hello, everyone. Let's all say welcome to Amy. Amy is the Illinois State Director for Math Kangaroo, and she's also the head of school at Vanguard Gifted Academy. That means she doesn't just handle Math Kangaroo, she actually runs the entire school. Recently, she moved from Florida. That's very interesting. You moved from Florida to Illinois. You're a brave person. That's all I can say. I grew up in Madison, Wisconsin. But in any case, sounds good. And she previously led initiatives for Math Kangaroo, local math circles, and gifted and science organizations. She is a graduate of the 2025 Math Circles Institute at the University of Notre Dame. With that, I'll pass it over to Amy. Amy, please pass it to Eli and Leo as we go on. But have a good time, everyone. Take care.
Thank you.
Bye-bye.
Hello, everyone. I'm excited to be here tonight. Before we get started, I wanted to share a personal story about our wonderful leader there that just hopped off. Years ago, when I was in Florida, I was attending a gifted conference, and I was sitting in the audience. We're getting ready for everything, and the person sitting next to me couldn't sit still, and he is hunched over a puzzle. And I can't remember if it was dice or a Rubik's Cube. He had something and he's working on it. He's so excited about it. And he's completely engaged. And he was having the time of his life. And it, of course, was Po-Shen. So it was right, he was right there next to me, and it was amazing. And so I looked up at him and I looked up at him then and same now. I'm so happy that I get to be on here tonight with him. And the same energy that he had at that conference, I have for Math Kangaroo. It's about the puzzle. It's about feeling, that you get math, that you could be persistent in it. It's my favorite program. It goes for all grades, all ages, all students, all levels. So it's for everybody. And I even have kindergartners that participate. And math is more than about rote memorization. And it's not just about getting to the answer quickly. I'm sure you guys all know. It's about creativity and persistence. And just like Po-Shen in the audience that night, the getting so caught up in a challenge that you don't want to stop until you figured it out. So as you go through the workshop, remember, don't be afraid of the tough problems, to use your creativity, keep trying and have fun with the puzzle, all of it. And we're proud of you guys to be in these. And we're happy that you're here. So let's dive in, and I'll turn it over to Eli and Leo. Thank you.
All right, thank you so much, Amy, for that awesome introduction of what Math Kangaroo is all about. And I guess we can get started with introducing each other. So first, the person on my right is named Leo Elieson. He is a two-time AIME qualifier, also a Quiz Bowl captain, and outside of that awesome math and science stuff, he also enjoys frisbee, biking, and origami. So everyone, please welcome Leo as my awesome co-teacher.
Hello, everyone. Okay, so the person who just introduced me is Eli Gold. He's a student at Princeton right now, studying math and music. Uh, he's a U.S. presidential scholar and two-time USA MTS Search Perfect scorer. Wow. Uh, Outside of live, he teaches for local math circle. He's also world class at percussion and marimba, featured by the U.S. Navy Band. And open invitation. If you can find him in person, you can challenge him to ping pong. Okay, warm welcome for Eli.
Yes, hello everyone, and I guess that means we can get started on these Math Kangaroo problems. First one is problem number 2 here from grades 3 and 4. I guess I don't actually have the problem statement on my screen, but you can see it on Leah's screen there.
Yep,
Maybe
right
we can
here. Or
keep them there. Yeah, so we have 3 arrows that are flying and 9 balloons that cannot move. When an arrow hits a balloon, the balloon pops, and the arrow keeps flying in the same direction. How many balloons will be hit by the flying arrows? Okay, well, if we look here, we just have to like follow the trajectory. Okay, well, it's white, so you can't really, my hand can't go through it, but like we can kind of just look. It looks like the green and the red here will be popped by the first arrow, so that's going to be 2. And then this one will pop the yellow and the blue there, so that's another 2. And then the one on the bottom will pop the yellow and the red, so that's another 2. So I believe our answer should be 6, which is option E. And
yeah, looks
let's
good to
see.
me. Let's take a look at the answer.
Ah, that's right. Awesome. Cool, back to you, Leo.
All right, cool. Okay, another problem, and this one is about folding paper. So Lucy folds a sheet of paper in half. Then she cuts a piece out of it as shown here. So the question is, what will she see when she unfolds the paper? And I think what we need to do here is kind of find which one's symmetrical along the middle and also has this pattern Lucy sees already on the right side and mirrored on the left. So, and just a reminder to everyone, write your messages to chat relay. That way they can appear on the screen right here on Eli's screen and my screen. Okay, back to the problem. So let's draw it out. I'll start by drawing out this full rectangle, and then Eli and I will add some details. Okay, first we've got this sort of half pineapple like curve on here, and it's got some bumps. But let's first add the pineapple. What do you think? Okay, got the pineapple sort of thing, and now we can add these 3 little like spikes on both sides. All right. I'm inclined to answer D because this one has all the features of Lucy's original sheet of paper, and it makes sense to me. What do you think, Eli?
Yeah, that sounds about right to me. I mean, it's just like the same thing, but you reflect it, and that's the picture you get. So like, it works, yeah. I don't think there's anything to overthink here. I think the answer is D, and it looks like that is the correct answer. So we have this nice, beautiful shape that you get just by folding it in half and cutting. And it's actually like a really cool theorem in math. I don't know if you've ever heard of this, but it's like the one-cut theorem, which says that if you want to make like any shape, like no matter what it is, any weird kind of thing that you want, it can even have like holes in it and stuff, then you just have to fold it a bunch and then make a single cut, and then you can make that entire shape. So it's pretty cool. All right, on to question number 10 from grades 3 and 4. Albert fills the grid with these 5 figures. I guess these are animals. See, a rhino, a whale, maybe, a frog, a ghost, and maybe this is a special type of flower, or it's just a flower, I don't know. Okay, each figure appears exactly once in every column and every row. Which figure must Albert put in the cell with the first question mark? Okay, so this is like a Sudoku thing, I guess. I hope anyway, because it's just column and rows have to have one of each. So we should just be able to make some deductions. Let's see. So like this is really, I'm just going to call them A, B, C, and D. Is that worth it? No, I guess we can just do it this way. So this column has these 3, so it's has rhino and dolphin in some order, but dolphin is already here, so it can't be dolphin. I'm just going to put R for rhino. Okay, this thing is a rhino. And that means this one must be a dolphin over here. Put D for dolphin. Now if we look at this row here, we have a flower, frog, dolphin, and a whatever that is, but we're missing a rhino. So this would be a rhino, and now we're finally done, because if we look at this column right here, we have everything except for a dolphin. No, we have a dolphin. We have everything except for the
ghost?
frog. Oh no, that's a frog. It's so hard to see. Yeah, it's the ghost. The ghost is there. Okay, so I'll draw a little ghost, something like this, and there's like eyes. There you go. That's the ghost. And the answer should be A. Let's see, is that the right one? It is. It's a very pretty looking ghost, I must say.
All right, cool. Let's go to the next question. Toby glues 10 cubes together to make the structure shown to the right. He paints the whole structure, even the bottom. How many cubes are painted on exactly 4 of their faces? Okay, well, I think we should just go through each cube individually. Let's start at this cube on the top. I think it's painted on 5, because we've got the top and we've got also each of the 4 faces. So not this one, but the one below it would have 4, because it's on the left, right, back, and front. So that's 1, and the one below it also has the same property. Actually, the way we can find this more efficiently is kind of all of the faces are going to be painted. So that's 6 minus the number of other cubes it's touching. So 6 minus 2 is cubes that are connected to 2 other cubes are going to give us the answer here. And because these cubes kind of go all together in a string, even though it doesn't go in a straight line, it kind of goes in weird directions. Actually, all except for the 2 ends will have the property of 4 faces being painted. So the answer for this one should be 8.
All right, let's see if that's the
let's
right
look.
one. Oh, I do see. The answer is C, and it is 8. All right.
Yeah.
Okay. On to question number 18 now. We have a bunch of weights, 10 grams, 20 grams, 30 grams, and 40 grams. And, okay, we want to know which of these things is 30 grams based on this diagram here. So we know that A plus B is less than C plus D, right? That's what this first one is saying, or bigger than, actually, because that's how weights work. Is if it's heavier, then it goes down. I don't know, maybe I was thinking of like negative mass. And then in this case, they're actually equal. Okay, B plus D is equal to C. And that's like all the information we have. But we know that we're choosing from 10, 20, 30, and 40. So we just have to see what works. I see that C is the sum of the other two. Now, okay, there's only like 2 ways or is there only one way this can happen? I mean, the smallest sum you can get is 10 plus 20, which is 30. So there's another way. You could also have 10 plus 30, which is 40. But those are the only 2 things that can happen. So, okay. Yeah, I'll just say like B, D are like 10 and 20, or 10 and 30. And C is either 30 or 40, depending on these 2 cases. And we also know that A plus B is greater than C plus D. Okay, well, C is either 30 or 40. So like C plus D is already like kind of big. If D was, say, 20, okay, then this would be at least 50. And this couldn't possibly be bigger than 50, because then it would have to be at least as large as 40 plus 10. So I'm guessing D has to be 10. That's what it seems like to me. Yeah, I'm pretty sure D has to be 10. That doesn't actually narrow things down in this case, though. So let's see. But if C is 40, then this is 40 plus 10 is 50, so this would be 20 plus 30. And that seems to work. I guess, I mean, is there like a more deductive way of doing this other than just like seeing what works? I don't know. But maybe there is. But I'm pretty sure I just like see a solution that works. So like, or maybe we have to actually see it could be one or the other. So maybe we do have to go through things. Okay. Well, certainly one solution that I see is that A is, let's see, 20. Yeah, B is 30. And then C is 40 and D is 10. If this happens, then A plus B, oh no, then it's equal to C plus D. So actually that doesn't work. Never mind. I forgot it had to be greater than. Okay, so A can't be 20. Or not that, but it can't be that C is 40. I think C has to be 30 then. Yeah, no, that makes sense. Because if C was 40 and D was 10, then it couldn't possibly be greater than. So it has to be 30. So okay, now we're good. C is 30, and that just means the answer is C. But we can go through and make sure the rest of it works. If C is 30 and D is 10, then A is C. I mean, there's probably multiple options for this. Well, no, there isn't. This is 30, this is 10, that means B is 20, so A is 40 and B is 20, and this does work. Okay, so anyway, we see that C should be the answer, and let's go check. Hey, it is. Double C. The answer choice of C is answer C, and that is the right answer. Cool.
All right, cool. Let's do the next one. Okay, we've got a bunch of squares and rectangles. So the large rectangle is made up of a number of squares of various sizes. The three small squares each have an area of 1. What is the area of the large rectangle? Well, here's a cool property about a square with area 1. It's got to be a 1 by 1 square. So we can already find some side lengths. I'll just fill them in on the diagram. So 1, 1, 1, and that makes this dark gray, not the darkest gray, but this pretty dark gray square is going to have a side length of 3. And then it means this next square, which is kind of medium gray, is going to have a side length of 4. Okay. And there's another less dark gray, kind of lightish gray, that I've got an arrow pointing to. It's got side length 7 because it's 1 plus 1 plus 1 plus 4. So side length 7. And now we can find the side length of this really large gray square. This one right here. And it's going to have side length of 7 plus 3 plus 1, which equals 11. Now that we've got all these side lengths, we have the side lengths of this whole rectangle, of these squares combined together. So one side is 7 plus 3 plus 1, so 11, and we can find the area by multiplying that by the width, which is 1 plus 1 plus 1 plus 4 plus 11, which equals 18. Okay, multiplying this out, we get 198. So yeah, the answer should be answer choice D, 198. Let's see if it's right. Okay, cool. Yeah, it is right. And
Very nice number there. I just like that it's 2 away from being 200. So close, but so far away. Okay, on to question number 24 from grades 3 and 4. Oh, we're defeating a dragon now. Okay, we have to cut off all the dragon's heads. So this is like, I don't know, I feel like this is like Percy Jackson or something. I feel like this was in that book. Okay, if he can cut off 3 of the dragon's heads, 1 new head immediately grows. Matthias defeats the dragon by cutting off 13 heads in total. How many heads did the dragon have at the beginning? Oh, okay, that's really interesting. So, yeah, what's the best way to do this? We know that if we cut off 3, then 1 more grows back. So that's kind of like taking 3 steps forward and 1 step back. So if you think about it, it's like, well, there's a bit of an edge case when there's exactly 3. Oh, actually, no, that's fine. But in general, it's like, you have to, you're doing like 4 steps to go 2 steps forward. To cut off 2 heads, you're basically cutting off 4 heads. So it's like twice as long or something. So if you're cutting off 13 heads in total, I think we can kind of almost just work backwards or something. Like it had 0 heads at the end, but then right before that, it would have one head, and then before that, it had three heads, and then before that, it had, let's see, five heads, because you cut off three and then one more grew back. And then before that, it had, yeah, it's just going to keep on adding two, because you like cut off three, but then one more grows back. So you're just like decreasing by two each time. And 9, and so on. So each time you're cutting 3, so here 3 were cut, 3 were cut, 3 were cut, 3 were cut, and then 1 was cut at the end. So it has to be 4 steps, right? There has to be 4 of these steps, and then the final step is cutting off the 1. So I think actually the answer would be 9, just by working backwards here. Because, and we can work through this just to make sure, but like 9, you cut off 3, but then 1 goes back to 7. You cut off 3, so like I can keep track. This was 3 heads. You cut off 3, 1 goes back, so that's 5, and that was 3 heads. And then we cut off 3, 1 goes back, that's 3, and we cut off 3. And then lastly, we get down to 1, and we cut off 3. And then finally, we get down to 0, and we cut off 1. So in total, we get 4 times 3, which is 12, plus 1 is 13, and that is exactly what we wanted. So I think our answer is B, which is 9. Okay, well, will it be B? It is B. Okay, so it was meant to be. Back to Leo.
Interesting. I thought when I saw this problem that if it has 3 heads and you cut them off, then you've already defeated it. But I guess it immediately grows back, and then you cut off the 1. Okay, makes sense. Next problem is about 4 cards lying in a row, and we've just got to the grades 5 and 6 level, so it's going to ramp up, but stick with us. Okay, which row of cards can you not obtain if you can only swap 2 cards? Well, I think we can do this one just by... Okay, I see a clever way to do this one. Let's look at this 1 card. If we swap 2 cards... Oh, that doesn't work. Hang on. If we swap 2 cards and it's not in its original position, it's going to be one of the 2 cards that got swapped. So in option C, option B, and option E, it's out of its original position. So now we've got 1 card that's been moved. Let's look at the 7 card. The 7 card has been moved in option A, option E. Yeah, those 2. The 0 card has been moved in option A, option B, and option D. And now for the 2 card. The 2 card is out of its original place in option C, option B, option D. Okay, so why did I just do this? Well, if we look at option B, it's got a problem. 3 of its cards are out of their original place. So that means we couldn't have obtained it by just switching 2 of its cards. So I'm going with option B.
That's a really, really clever way of doing it. Yeah, I kind of just like looked at each of them and then saw if I could swap or not. But like you kind of like actually managed to find it and like also kind of prove that it couldn't possibly have come from swapping by like giving this interesting argument that 3 of them were in the wrong place. So that's a really cool way of doing it. Let's see, is it the right answer? Yeah, it is.
Okay, good.
Nice job. On to question number 3 from 5 and 6. Alice has 4 pieces of this shape. Pretty boring shape. Okay, it's just 3 things in a line. Which picture can she not make from these 4 pieces? Okay, so I think, do all of these have 12? Yeah, I mean, we know that there should be 3 times 4 equals 12 blocks total. So as long as all of them have 12, we can't actually use that information. I think they all do, so okay, that's just something to keep in mind. If there was a choice that had like 13 or 11 of them or something, then we would be able to choose that one. Let's see, I can definitely make A. I just do something like this, and then this, and then this, and then this. So like these 3, these 3, these 3, these 3. So that definitely works. I can get rid of A. Option C, oh, this one's kind of interesting, but we can still do it. We put first 3 there, second 3 here, third 3 here, and the fourth 3 here. And so we can do C, get rid of that. I can definitely do B as well. I can do something like this, 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 this. So that takes care of B. Get rid of that. Now we're left with D and E. And I have a suspicion, but let's see if I can try D first. Yeah, I think this one works. Because I can start at the bottom here, get that one, get this one, get this one, and I get this one. And so that also works. And so, of course, it's the last one we try. As always seems to be the case when you're doing process of elimination. But let's see if we can try to give an argument as to why this can't be done. Certainly, in order to get this one in the corner here, it has to be like this. There has to be 3 in a row here. There's just nothing else we can do. Same thing with this one here, and same thing with this one here. And so, okay, well, that only leaves us like these 3 blocks left. And they're not in a line, so there's kind of just nothing we can do. But you can see, like, we kind of needed to put these 3 there, and so we were left with something that was impossible. And so this is actually like an actual proof that it's just, we can't make a shape from things like this. I guess we're not allowed to like cut the shape or whatever, but oh well. Maybe Alice doesn't have scissors handy, but looks like option E is our choice. And oh, it's like kind of like a spaceship or something, and maybe it like, I've just given it like rooms in the spaceship, and I don't know. I can kind of imagine this like being something in like an old video game. Okay. Let's see if E is the correct answer. It is. Great. Back to you, Leah.
All right. Cool. Okay, we've got a problem about traffic flow. Sounds boring, but I can assure you it is exciting. On a planet, there are 10 islands and 12 bridges. All bridges are open for traffic right now. What is the smallest number of bridges that must be closed in order to stop all traffic between A and B? And don't worry, I've got a larger map. So I got my trusty planet map up here, and let's see. I can already, just looking at it, I can spot a way to get from A to B, and so it would be taking this path I've highlighted here. Okay, so we kind of start on A, go down 2, and then go right 2. And also, there's another path which doesn't use any of the same bridges. And let me check the problem statement, but I believe the question is, what is the smallest number of bridges that must be closed? Yeah, that's right. So because I've made 2 paths that use completely independent bridges, if I shut down a single bridge, it can't shut down both of these paths. So the answer cannot be 1. It's got to be more than 1. And I actually see right now a way I can shut down 2 bridges, which will shut down all of the travel between A and B. So if I target these 2 bridges, so there's one kind of near the left, and there's one all the way up here, it will not just shut down these 2 paths, but actually all of the paths, because there's kind of only 2 ways to get around this island, or get around this planet. Apologies. So I'm convinced that it's answer choice 2, or answer choice B, which is 2. Okay, let's take a look at the answer. Oh, yes, and indeed it is B. Okay.
Awesome.
Another problem from Eli.
Indeed. We're on to question number 7 now. 5, 6, and 7. Okay, a special die has a number on each face. The sums of the numbers on opposite faces are all equal. 5 of the numbers are 5, 6, 9, 11, and 14. What number is on the 6th face? So it's a really weird die. The numbers are just random, it seems like. But we know that the sums of the numbers on opposite faces are all equal. And that's actually something that's true about real dice, which is kind of cool. If you ever, take a die, you'll see that like the 1 and 6 are opposite, the 3 and 4 are opposite, and the 2 and 5 are opposite. So all the opposite sides add to 7, which is it's like just kind of a neat fact to know. And it's also a way to like find a fake die, maybe like a counterfeit die or something, because it'll have like the wrong order of faces or something. All right, so we want to know what's the number on the sixth face. There's probably a few ways to do this, but we know that, let's just call that sixth face x. We like pair them up or something. I mean, if we find the sum of all of them and then divide by 3, that would give us the sum of each of the two opposite faces. We can do something like this. I don't know exactly if it'll work, but let's see. 14 plus x, so the sum of all of them, and then you divide this by 3, and that will give you the common value for each of the pairs. So what do we get? This is 11, this 9 is 20, 31, 45 plus x, so that would be 15 plus x over 3. And this is the common sum for each of the pairs of faces. Okay, cool. So what do we do from here? Let's see. I guess we can just try to see like which two faces can actually be opposite. Because, okay, if it's like what can 5 be with? Certainly it couldn't be with 6, right? Because then it would be less than 15. And 9 certainly couldn't be either. 11, well, if it was 11, then you'd get 16, which has to be 15 plus x over 3. That would work if x is 3. I guess we could just like try each of these. There must be like a more clever way to do this. But I just don't see it. So, Leo, do you see a clever way to do this? Because I know that this will work, but
yeah, I do see a clever way. So if we are, I'll write up the same expression that Eli had on his screen. It's 15 plus x over 3. Because we know they add up. They're all integers because we have pairs and 5 of them are integers. So at least one pair has to be. These 2 integers. Integers are closed under addition. So we have to have, or that is when you add 2 integers, you get another integer. So we know that this x value has to be a multiple of 3. So it can't be 4, can't be 7, can't be 8, or 13. Actually, it has to be 15 just from this property right here. So
I mean, like, yeah, that's very clever using the answer choices, but like, yeah. I mean, I guess I don't know. I was thinking like if you didn't have the answer choices, maybe this would be. Is there like a clever way to do it then? I don't know. But
I don't know.
Maybe this was actually written with the intention of using the answer choices because, like, did they really decide to make none of the other ones a multiple of 3? Like, I don't know. I think maybe it was actually like an intentional use the answer choices type of question. But if you wanted to do this a different way, I think the way you would do it is just by like trying all the pairs and like seeing what values you get. So like I was just gonna say like 5 plus 11 is 15 plus x over 3, and like see what happens. And then 5 plus 14 is 15 plus x over 3, and then just try each of them. And then also the last one is 5 plus x is 15 plus x over 3, and then just see what happens. And then you'll get different values of x, and then some of them will work and some of them won't. So there's really only 3 cases to try. It wouldn't take that long, but
yeah.
Okay. Anyway, let's see if E is the right answer. And it is. Huzzah. Okay, back to you, Leo.
All right. Okay, I got a bit of a meta problem here. In the time it takes Peter to solve 2 problems for the Math Kangaroo competition, Nick manages to solve 3 problems. In total, the boys solved 30 problems. How many more problems did Nick solve than Peter? Okay. We can, well, let's say it takes 20 minutes. Wait, no, that's not right. Let's say it takes some period of time called X. During this time, Peter solves 2 problems, Nick solves 3 problems. More importantly, together they solve 2 plus 3 equals 5 problems. Therefore, total, it takes 6 periods for them to solve 30 problems together, because 6 times 5 is 30. Each period, Peter kind of goes ahead of Nick by 1 problem, because he solves 3 problems when Peter only solved 2 problems. So during these 6 periods, Nick widening the gap by 1 each time, we get 1 times 6 is answer choice B, 6. And let's take a look. All right. Yeah. That is correct.
Yeah, that was a very cool way of doing it. I guess it's like as if Peter and Nick were like working together, and so their combined rate was like 5 problems per minute or whatever. And so then it takes like 6 minutes, and then you can do it that way, which is good, kind of cool. I mean, the other way is, of course, like I don't know, the naive way of doing it, setting up an equation and then solving. But
Mhm.
that's like a really cool way of doing it because it's like you can imagine that they're like both painting a house together or
Mhm.
something, like working together to solve a problem. All right, on to. Oh, wait, was that the last question? Oh, we're
I
so
think
early.
I think that's it.
Oh, wow. Okay.
Hmm.
Well, if anyone in the chat has a math problem for us,
Yeah.
you
We'll
can
take
send
some
it.
problems. Remember, so
Uh,
sending the chat relay. We're accepting problems, and please nothing too difficult. We only have 25 minutes left.
yeah. Oh, we
Um,
may just end the stream early. We'll see.
yeah, we'll see. We'll see.
Uh,
Got some arithmetic problems. No, thank you. Hmm. Ooh, got a problem from Olivia. What do you think? All right, just kind of taking this problem to the next level. We have 1 plus 2 plus 3 plus 4 all the way to 10. Now, this one you can probably do by hand, but there's a famous mathematical story. I think, was it Gauss? Am I thinking of Gauss?
I
Uh,
think you are thinking of yes.
yeah. So if you add up, so Gauss was bored one day because his, or he finished all his work, I guess, and his math teacher told him to add up one, all the numbers from 1 to 100. But Gauss accomplished this really quite fast. So uh, he used like a special technique to do this. And Eli, would you like to explain this technique?
Yes, I don't know exactly how Gauss phrased the technique, but I can show it the way that I think about it. So we have 1 plus 2 all the way up to 10 in this particular example. One kind of like really clever thing I can do is to pair them up. So, I have 1 and 10 there, right? And 1 plus 10 is 11. Okay. I also have 2 and 9. So I was just like going in reverse almost, like starting here and just working my way inwards. 2 plus 9, well, that's also 11. And
Hmm.
okay, well, I can keep on going with 3 and 8. Well, 3 plus 8 is also 11. Okay, I think I see what's going on. How many of these 11s are we going to get? Well, we pair up 1 and 10, 2 and 9, 3 and 8, 4 and 6. The last one is, well, 5 and 5. Well, not quite, because 5 only happens once. Oh, no, it's 5 and 6. Never mind. I'm so wrong. It's 5 and 6. There we go. So it's 4 and 7, 5 and 6. There we go. I guess I was thinking of the example with 1 to 9, but 1 to 10 also works. And so we get 5 plus 6 is 11, and that's the last one. So we have 1 to 5 as like all the pairs that we get. And so in total, it's 5 times 11, right? This is just a bunch of 11s added together, and there's 5 of them. And so we get 55 in a very clean fashion. And so, Leo, maybe you want to talk about like the general case.
Oh yeah, sure. So, well, right before the general case, there's a. I want to show how Gauss, uh, like, solved that math problem and shocked his math teacher so quickly. So we can kind of do the same thing Eli was doing with pairing up 1 plus 100, 2 plus 99, 3 plus 98, etc. And how many of them are there? Well, it ends at 50 plus 51. Easy to count these because they just go 1, 2, 3, all the way to 50. So there's 50 of them. And the sum of them is all the same. The sum of them is all 101. So it would be 50 times 101. Okay, and now for the general case. Let's say we're adding up some numbers from 1 to n. Seems reasonable. We can pair them up 1 plus n, 2 plus n minus 1, 3 plus n minus 2, all the way to, I guess, and there's a bit of an even odd case, right?
Yeah, so one way you can get around that, if you're like even more clever, is just say like x is 1 plus 2 all the way up to n. And then x is also n plus n minus 1 all the way down to 1. And so then you add these two together, you get 2x is, okay, this first term is n plus 1. The second term is n plus 1, right? 2 plus n minus 1. And you keep on going. They're all going to be n plus 1, including the last one. How many terms are there? Well, we're just counting 1 to n, so there's n terms. So this is n times n plus 1. And so our sum is n times n plus 1 over 2. And we didn't have to do any weird, even, odd things. But in practice, I mean, I just kind of visualize it better if you're like given an actual sum. If you like just pair up the terms and like kind of makes more sense what's going on. This is kind of just like a neat algebraic trick. But all right, I think we're gonna close the live stream now because, well, we're done with all the problems. So goodbye, everyone. Thank you so much for coming to this Math Kangaroo live solve. Hope you enjoyed. And yeah, hopefully you keep on coming to these. They happen every month. And I'll see you around.